Good morning. My name is Jean-Pierre, and I am going to be presenting the magnetic properties of silicon carbide. So, some general information first. Silicon carbide, also known as carborundum, is a compound of silicon and carbon. Uh, Silicon carbide is a semiconductor material and is commonly used as an emergent material for applications in semiconductor devices, playing a key role in industrial revolution, and is still widely used as abrasive and steel additive for structural ceramics. Known primarily through its structure, silicon carbide is a hexagonal is a hexagonal structure with a coordinated tetrahedron and is commonly also known as having the word side structure. Aside from having its bonding type being covalently bonded, its chemical formula is silicon and carbon and is commonly linked to having high and strong covalent bonding, normally used for abrasive and smoothing materials. It is also one of very few kinds of ceramics that have a type of structure called polytypism, also known as having non-stoichiometric differing orders of one-dimensional sequences. This means that the crystal structure exhibits a number of different one-dimensional ordering sequences without any variation in stoichiometry. Although a great variety of silicon carbide polytypes is known, it has become accepted practice to refer to the cubic polytype as BSIC, and to all non-cubic structures, hexagonal and rhombohedral, collectively as SIC. There are many interesting uses for silicon carbide, predominantly its interfacing with interesting electrical properties due to its semiconductor characteristics, of which the resistance of different compositions varying by as 7 orders of magnitude and higher. It's used in manufacturing of fast, high temperature, and high voltage devices, and is also used in the manufacture of electronic appliances such as light emitting diodes, LEDs, and detectors. Of many other interests that silicon carbide can be normally known for, its usage is also very strongly applied with magnetic properties, as will shown later. Silicon carbide is very important to the usage in electronic devices, such as with semiconductors, circuit boards, and is commonly used as capacitors in one respect. It is vective because of its capability to be doped by N-type by nitrogen or phosphorus and P-type by beryllium, boron, aluminum, or gallium. Its metallic conductivity has been achieved by heavy doping with boron, aluminum, or nitrogen. Silicon carbide is a dielectric ceramic, also called an electroceramic. Electroceramics are a class of ceramic materials used primarily for their electrical properties. Other dielectric ceramics are strontium titanate, calcium titanate, magnesium titanate, calcium magnesium titanate, and others. Historically, development in the various subclasses of electroceramics have paralleled the growth of new technologies. Examples include ferroelectrics, high dielectric capacitors, non-volatile memories, ferrites, data and information storage, solid electrolytes, energy storage, and so on. So, what do we mean when we say dielectric ceramic? A dielectric or dielectric material is an electrical insulator that can be polarized by an applied electric field. When a dielectric material is placed in an electric field, electric charges do not flow through the material as they do in an electric conductor, but only slightly shift from their average equilibrium positions, causing dielectric polarization. Because of dielectric polarization, positive charges are displaced in the direction of the field and negative charges shift in the direction opposite to the field. For example, if the field is moving in the positive x-axis, the negative charges will shift in the negative x-axis. Commercially manufactured capacitors typically use a solid dielectric material with high permittivity as the intervening medium between the stored positive and negative charges. This material is often referred to in context as the capacitor dielectric. The most obvious advantage to using such a dielectric material is that it prevents the conducting plates on which the charges are stored from coming into direct electrical contact. More significantly, however, a high permittivity allows greater storage charge at a given voltage. Dielectric materials used for capacitors are also chosen in such they are resistant to ionization, allowing the capacitor to operate at higher voltages before the insulating dielectric ionizes and begins to allow undesirable content. In silicon carbide, there are many researchers that fixate on its magnetic properties and hardened tenacity against handling otherwise unsavory properties and thermochemical conditions, such that it is invited quite the large accrue for research for their electromagnetic properties and applications within and across the industry. Such as with Chabi Kadel's paper, Two-Dimensional Silicon Carbide, the Emerging Direct Band Gap Semiconductor. By comparing band gaps from electronic band structures of graphene, silicene, silicon carbide, band gap had increased substantively compared to the first two polymers. That as the thickness of SiC nanosheets decreases from 9 to 3 nanometers, the saturation magnetization increases. The formation energy, configuration, structure, stability, and thus properties of these structures is highly affected by the atomic ratio of silicon and carbide and whether the structure is carbon or silicon rich. Given their tunable direct band gap in the range of about 0.5 to 3 volt, the next generation of electronic and optoelectronic devices can benefit largely from the discovery of 2D silicon carbide. Importantly, the properties of 2D 6 silicon carbide can be tuned by external stimuli such as the electric field, strain, defects, and chemical doping. Moreover, silicon carbide offers tremendous potential for chemical sensing, quantum technologies, and energy storage for conversion devices. These potentials and properties reveal how huge the emergence of 2D silicon carbide will be. Thank you. That was my presentation. Thank you.